Hello guys, today's video is about positional encodings in the paper Attention is All You Need, which was one of the key papers in creation of transformer architecture and further development of BERT and GPT models. And when I was studying this paper about 4 years ago, I quite well understood how attention works and all the other things, but I didn't quite well get how positional encodings work and what are these tiny details on how they affect attention, etc., etc. And now I just spend some time diving deeper in these things and want to share with you the intuition and the knowledge that I get out of this dive. Basically, this video is motivated by the fact that when I was reviewing different videos and different papers explaining how positional encodings are implemented and how they affect the results of the model, I was not satisfied by some of the answers. They seemed too superficial to me, and I tried to dive deeper to understand, okay, how exactly it works and if the answer is exactly the same as you guys say. And for some things, I found that answers are not that obvious as it was initially presented, and I want to share all these things with you today. And I will use Miro board for visualizations. I have prepared some plan here and some visualizations here. Also, I will show you some things in the notebook, Jupyter notebook that I've prepared in Google Colab with you, and I will share this notebook with you and put it in the description, so you will be able to review it by yourself and play around with it. And also we probably will look into the original paper and into this awesome annotated transformer paper, which contains the text from initial white paper plus some annotations, code snippets, and other explanations. But the key plan for us will be here on Miro. And the plan is the following. So first of all, all this speech will be for people who know what transformer is, but want to understand how positional embeddings are implemented in the original design of the transformer, which was presented in the white paper, or for those who just want to understand how positional embeddings encodings can be implemented. This speech will mainly be about Attention is All You Need paper, because in BERT or GPT model, positional information is added through some other mechanism. I will tell about it briefly, but the main focus will be on how it was designed in the original paper. So first we will speak about how encodings are different from embeddings, because these terms are quite similar but have a bit different meaning, and sometimes they may be confused. Then I will speak about why I think positional encodings are needed in the transformer, because the answer seemed to be quite obvious, but it was not that obvious to me, and I found some details about that, want to show you them. Then I will explain and visualize the positional encodings formula, like what is the intuition behind that, what it looks like. So there are some visualizations in the internet that I found, but they were not that good to build good intuition, at least for myself, so I hope it will be helpful for you also. Then I will show you how encodings are added to the input, what is the mechanism and what is the result of that. And then we will look into what places inside the transformer architecture are affected by positional encodings. So what is the exact effect of these encodings? What is the mechanism of them influencing the attention? And then there will be the summary with some limitations and summarization of key things that were in this explanation. So let's dive deeper. And first thing that I want to speak about is what's the difference between encodings and embeddings. And mainly, word embeddings is used to say about a thing that stores information about word semantics. And usually it's a dense vector of values. Not sparse one with lots of zeros, but a dense one with almost all the values filled with non-zero value. And we can say embeddings or semantic embeddings of the token or of a word. Positional encodings store information about word position in the sentence. Though encodings exist not only for positions. So for example, you may have heard about such thing as one-hot encoding. And one-hot encoding is basically an encoding. It's called encoding, though it may it may be used to store information about the semantics of a word. Though it will be a sparse vector in this case. So here you see that embedding is a dense vector, and encoding, one-hot encoding, will be a sparse vector, even though it represents the semantical information. It means that embeddings doesn't necessarily mean that it relates to semantics information. So encodings may also be used to represent semantics information. And also, I've heard that the result of the encoder sometimes also referenced as encoding. So in transformer architecture, this block, which is encoder, produces some vector, and this vector and output of the encoder may be referenced as encoding, which is a bit confusing, because my basic intuition was that encoding is a simple thing that is produced by the formula, and embedding is more complex thing that is produced by neural network layer, which is, like, in many cases correct, but this result of encoder referenced as encoding confuses this formulation a bit. So I would say that embedding is a vector that produced by a neural network layer, and encoding is a vector that produced by a formula, or sometimes encoding may be also the result of encoder, which is even a more complex thing than embedding. But in this particular paper, when authors say encoding, they mean positional encodings produced by the formula, like sine and cosine formulas. So the encodings are not used to reference the result of encoder. Okay. Let's move forward. And the next question that I was reviewing and analyzing is that why are positional encodings generally needed in the architecture, given that tokens in the input already go in some order. So I was initially thinking like, okay, tokens are provided in some order, and authors say that we need to inject positional information just because it's not stored. But basically it's stored, there is some order of tokens. It's quite obvious that recurrent neural networks take care of order just because they process token by token, right? So they process one token, produce some vector, then they process next token, produce some vector. And this sequential processing already takes care of the order. And convolution neural networks, as authors say in the paper, has this kernel that is position aware. So kernel applies like first number to first token in the window, second number to second, third to the third. So it's also quite obvious how convolution neural networks take care of the position. But in transformer we have matrix multiplication operations, and I was just surprised by the fact that this matrix multiplication doesn't take care of the position information. So I want to show you how exactly it doesn't care of the position. So that's the general transformer architecture, and this block multi-head attention is presented here. So these are screenshots from the original paper. And this scale.product is present here. And in this architecture, we have two types of layers. First type is multiplication of the input by some matrix. So it's a fully connected layer. And second type of layer is this mul here, which multiplies a matrix representing input, like current state of embeddings, with matrix representing current state of input, so like multiplying Q by K or multiplying the result of these by V. And I want to show you how exactly positional information is not taken into account here. So first of all, when you have such a matrix in linear layers, and by the way, linear layers are present here when we make projections of input into smaller space of V, K, and Q. And there is also a linear layer here, and there is also a linear layer here. So there are several linear layers in the architecture, though all of them work the same. So here is the visualization of the result. Let's say it's the vector representing embeddings, and the color, blue color here, means that all these numbers relate to one token, and all these numbers relate to second token. And when these matrices are multiplied, the result also is separated per token. So this result is only produced by the first row, this is by the second row, etc. So you will also see this visualized here. So there is a great resource, matrix multiplication.xyz, which makes a visualization of how exactly it works. So we have this matrix of learned weights, and then when they're multiplied by our input, we multiply entire column of the second matrix by the row. So this number is just the result of first token embeddings and this transformation matrix. So you see that we don't combine information of several tokens here. And then again, second column with the first row to produce this number, and this number is the result of second row, like second token. And when we do this step by step, we see that, okay, yeah, really, this row is produced only by this row and this matrix. So no rows are confused, which means that if rows will be reordered, the matrix will be the same. The only thing is that the order of values will be a bit different, which means that there will be some position information. So when next matrix multiplication will be applied, values will go in different order and will be multiplied by like a bit differently, though this difference, I mean, is probably not what we want, right? So it's just the reordering of the numbers in the vector, and it's quite hard for the model to extract information on that. Okay, these reordered numbers mean that they are in different position. And second type of layer that we have is this multiplication, where we might multiply projection of embeddings on another projection of embeddings, and it works in this way. So we have this and this, and when we multiply them, we have matrix like that. And in colors, we see that, okay, this is the combination of blue and blue, this is the combination of blue and green, etc., etc., etc. So again, if we reorder some values here will also be reordered, but their magnitude will be same. And probably there is a way to extract information from reordered numbers in the matrix, but it's still hard for the model to use it. So likely not what we want. So I would say that there is some positional information because values are reordered in the matrices, but it's hard for the model to use this information. That's why we need some additional way to inject information about positions. And I will show a bit later how it's injected and how attention is amplified by this mechanism. And there are some additional benefits of adding the attention, the positional encodings in the architecture. First of all, what authors say about is that they had a hypothesis that the way they added encodings in the architecture will allow them to extrapolate to longer sequence length. So for example, if they trained model on sequence length of 1,000 tokens, probably because of these encodings, they will be able to infer on sequences of 2,000 tokens. And yeah, it might work potentially. Then the way they have implemented attention amplifies, like from the beginning without any learning, amplifies attention to nearby tokens. I will show you how it works. Also, if positional information is inserted in the tokens embeddings, potentially we can change, reorder the tokens in the sequence, thus doing data augmentation and train the model with this augmented data. I'm not sure if authors tried that, but there is some potential for that. Also, potentially what we can do is we can, if we, for example, have sequence length of 500 tokens and our inputs are small, we can combine several inputs into one sequence. Each input will have positional encodings starting from 0, and we can pass this entire sample produced out of several samples into the model, thus training on multiple samples in one run, thus speeding up the learning. So we will need to play with mask in the attention a bit, but it's possible, and I'm not sure if somebody has done that, but there is also some potential for that. In this case, if positional information is stored inside embeddings, then we can just do that, the thing that I said about. Okay, so let's move forward, and the next thing is the heart of the entire embedding encoding idea, how the formula works and what it is. Let me show you. So first of all, the formula is presented in the original paper. It's highlighted here. So we calculate even indices of the encoding using sinus and odd ones using cosinus. I will visualize them in a second so that you will see what they look like. But what you already may notice that these encodings don't depend on the input. They are determined by the sequence length. So if we will have different input but same sequence length, encodings will be the same. And even if the sequence length will be higher, first positions will have same encodings. Okay, and also I will show you first visualization here what the actual values of the encodings will be. Let's say we have a sequence of I love you Earth. Then encodings for that will be calculated in this way. For first index of encoding, it will use sinus, and 2i will be equal to 0, and thus this formula will result in this vector. So this is for position 1, 2, 3, 4, etc. Then for encoding index 1, we will use cosine, and it will look like that. Then for index number 2, we will again use sinus, but with 2i equal to 2 here, and then cosinus for next one, and etc, 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 till we get to D model index, which is 512 by default. Now let's go in the notebook and I will show you what it looks like visually. So what I have here is I have a notebook that first produces the data frame with column J, and by J I mean the index of the encoding, and it's not I because in this formula we don't have I, we have 2i, and index encoding index 0 corresponds to 2i equal to 0, in this case I equal to 0, and encoding of index 2 corresponds to I value of 1, though it's encoding index 2. So we will look into 2i value and into j value, and j may be either odd or even. So just to have an ability to look exactly in the index of the encoding, I have this j column. Then I calculate 2i based on that, and here is it, j and I. So it's 0, 0, 2, 2, 4, 4, etc, etc. Well, j is just incrementally increasing. Then I just distinguish if it should be sine or cosine. I have a column for that. And then I calculate the power thing. Power is, let me show you this component, 2i divided by d model. And then I calculate entire denominator, which is 10,000 in the given power. So calculate them. And let's look into what they look like. So 2i thing first is a linear progression from 0 to, in this case, 512. So maximal index of the encoding, it's actually 511 because we start from 0. And power is almost the same thing, though it's now normalized from 0 to 1, right? And you see a slight slope here. It's just because we do this 2i transformation. So we just, in case of odd value, we just treat it as this odd value minus 1. Okay, so this is here, and then denominator has this progression because denominator has a power, so it's 10,000 in the given power. We see this exponential progression, and on a log scale here, so here is the log scale, it looks like a straight line, which is expected. So that's what denominator look like. And then I calculate the value of encodings for different positions, for positions from 0 to 1000, and then with some step for next positions, and then for late positions also, just to just see how this vector of encodings behave itself on different position numbers. And let me show you what it is. So scrolling down. Okay, so first of all, let's look into the value at particular encoding positions. So if we take first value of the encoding, it will have this period. So it is sinus with high frequency. So it just oscillates from -1 to 1. And probably we can also look at the big scale first. So let's look into max position from 100,000 and see what it looks like. And then we will scale back to, so if we take many positions, we see that the frequency is super high, and then frequency at this position will be like lower, right? So we see that at the maximal embedding position of 511, we have a period, the maximal period of about 60K, and then the value starts to repeat. And initially, to me, it seemed like, then our encodings will start to repeat completely, starting from position of 60K. But in reality, it doesn't. I will show you later why. But for now, the first piece of intuition is that first, encoding indices have high frequency and later have lower frequency. And the maximal period, the longest one, is about 60K, and then maximal period starts to repeat. So let's get back to a smaller number of positions and see some nearby values. So here is the period of encoding at position at index 50, and here is the period of position 51. This one is sinus, this one is a cosinus, and you see that they have the same frequency. Cosine is just shifted a bit, right? And I haven't said that. Let me show you this thing. So what this graph basically shows is that if we have encoding at position 50, what will be its value for, let's say, position 100? So for position 100, it will be 0.16. And what will be its value for position for next token? And for next token, it will be hard to zoom in. Let me show you. So here is for 100, and here is for 101. So for next token, its value will be a bit smaller, right? So here is 0.16, and here it will be minus 0.24. And for next token, it will be minus 0.6, etc., etc., etc. So this graph is pivoted like that. Let's move forward, and now I will show you what it looks like for particular positions. So at the moment we were looking at encoding indices and plotting it over positions, and now let's look at particular positions and have a plot over encoding indices. So for example, for first position, value over depth of the encoding will be like that. So sinus for 0 will be 0, and we have like 0 everywhere, and cosine will be 1 on all the positional encodings. For next position, we will have some behavior here, so some change. And the deeper we go in positions, the more frequency we will have here at the beginning. Though it will not be symmetrical, because you remember that power changes exponentially, right? So that's why we have higher frequency here and lower frequency here. And if you go further in the position, so see cosine for position 10 has this pink frequency, and sine for position 50 has more oscillations at the beginning. And again, this low frequency here. And the deeper we go, the more frequency we see in the beginning, even more here, right? And at position, let's say 10,000, we see quite a high frequency during almost entire encoding scale, though still not that high frequency in the end. And for position 661,000, we will see high frequency everywhere. And the thing that I was surprised about is that encodings won't start to repeat after this position 61,000. because only this latest value have a period of about 60,000, but this index has lower period and it will oscillate with its own frequency. And actually it will be really hard to find some position starting from which all the periods will start to behave the same as they behave from the beginning, because these periods are just different. And it will be really a high number of positions when entire vector of encodings will start to repeat themselves. And that's the first thing that I heard in many videos, and people say just, yeah, period will start to repeat. In fact, it won't. Okay. And next thing, let me look in the agenda. Okay, so I'll show you that. Yeah, next thing that I want to show you is how does it come that higher attention with this formula of encodings, higher attention is paid to nearby tokens. How does it work? And I have this visualization prepared. You may have seen it already. So I'm showing dot product here, but sometimes people show cosine similarity, which is almost the same thing, to see how multiplication of encoding vector at given position. So what will be the dot product of encoding at given position by encoding at some other position? And as expected, dot product is the highest on the diagonal. So if you multiply vector by itself, you will have the highest dot product if the magnitude of the vectors are same. And as you see, we have still quite high value on nearby positions. So if we multiply position 200, embedding for position 200 with the embedding for position 210, the result will be almost maximal. Why? Just because the embedding vector looks almost the same, so higher frequencies, the beginning will be different, but the tail of the embedding, the lower frequencies, will be about same. That's why if we just go a bit from our position, dot product of encodings will be about the same, because a small number of encoding components are changed. And the more the distance, the more frequencies will have different values, the more components of the encoding will have different values, and thus dot product will decrease. I will show you a bit later why it results in higher attention, but at the moment you can just remember that dot product is higher for nearby positions, and the mechanics is as I have explained. That's an important thing. And actually, that's the reason of why sine and cosine were selected. There might be other formulas, but sine and cosine basically are changing gradually, and they have this frequencies thing, and that's why they naturally result in dot product to be higher for nearby positions. And yeah, we will look deeper in this mechanism on the next frame, but for now let me highlight one more thing related to the formula that was not that obvious to me, and I just understood how it works and have the explanation here. So in the paper, authors say that they have selected such a formula because for any fixed offset k, positional embedding for pose plus k can be represented as linear function of position embedding for pose. I didn't quite understand what exactly they mean by linear function, and here I have the explanation of what it means. So as you probably remember from math course, we can transform this formula of sinus of pose plus k to this formula, and for cosine we can do almost same transformation. And how can we potentially do this in the transformer block? That's the question. What I thought of is here. So let's imagine we have these encodings vector. In reality, there will be added to embeddings, but for now, for simplicity, let's imagine that we have just encodings as the input. And then we have these projections over here in the transformer before the attention. So we have these projections, and these projections may be learned in this way. So they may have corresponding sine and cosine values to have this right components of k divided by the denominator, so this might be learned, so that if we will multiply these encodings by these corresponding values, we will get shifted encodings. So in this case, if we multiply this matrix by this, we'll have this. And as you see, values actually match. So for first position, we will get vector which looks exactly the same as pose 3, so shifted by 2. And for second, it will be shifted to pose number 4. And then when doing multiplication, this vector will produce highest dot product when multiplied by this vector. So like higher attention will be paid to this thing. I will show you a bit later how exactly it's done. And yeah, I think that it's quite possible for the model to learn it and to shift the entire positions by required offset. And you may actually check that it actually works correctly, because sine and cosine values here were taken from here, because actually they're sine and cosine for position 2 as we do shift by 2. So we can just validate it. It works correctly. And that's also the reason of why both sine and cosine are present in the encodings, because they allow to do this beautiful offset by doing the matrix transformation. Initially, I thought that probably they meant multiplying by a number by this linear transformation, but actually they meant by multiplying by a vector, but this vector can be learned. That's still a question if model actually learns this vector, I don't know, but there is a potential for that. And yeah, I've also made this in the notebook, as I was just curious if it actually works this way. So what I did is I prepared these vectors of sine for position 300 multiplied by cosine for position 200 to see if this will actually result in embedding vector for position 500. So I've prepared this, and then I've made the visualization, so I will show you what it looks like. Okay, but I will just adjust the size so that I will be able to click legend here. Just wait a sec, because I found out that it actually works, and I just during the math course in the school I didn't think that it will be that handy for me in the future, but in reality it is. So I have sine and cosine for different positions here, and then I have their multiplications. So see, let's say I will put a sine for 500, and then that's what sine for 300 multiplied by cosine for 200 looks like. So it isn't that symmetric as this one, right? So there is some amplification here, some reduction here, and that's the where is the second component? Here is the second component. And when we sum them up, let me show you what happens. Actually, we have the same vector as sine for 500, right? So I enable this one, and we see that, yeah, it's just the same. Lines are completely overlapped. And the same happens for cosine. So we have cosine for 500 here, and have this cosine for 300 multiplied, etc., etc. And then we have again the same vector. So yeah, usually I just check that yes, it works. Looks exactly as expected. Okay, and yeah, probably that's all I wanted to tell you here. Let's move forward. Next big block of explanation is how encodings are actually added in the vector of the input. And initially I thought that encodings are concatenated, like for example, have embeddings of vector 512, and we add 512 encodings vector to the end, so that we have 1024 values in the input. But in reality it's not. They're just added by add, just summed to corresponding components, so that if you have embedding of 512 and encoding of 512, we have the result of 512, just summed up by component by component, number by number. And the question, my question was like, okay, how doesn't it impact the semantical meaning of the tokens? How doesn't it harm the learned embeddings? And in reality, they have some impact, but not that high as I expected. Because my initial thought was, okay, we have embeddings from -1 to 1 and encodings from -1 to 1. We sum them up, and embeddings are completely masked with this about same magnitude vector added. But in reality, in the paper, authors say that embeddings are multiplied by square root of D model value. So they say it over here in the original paper. In the embedding layers, we multiply those weights, which means the weights of embedding layer, which produces semantical vector, and they multiply them by square root of D model. And in annotated transformer over here, we see the code for that, and actually it's done like that. So they have this layer, and then when they apply this layer to the input, they multiply the result by square root, right? So it works as I said, which basically means that the magnitude of vectors will be different. And here I have an example of what they will be. So these are 3 tables, one of them showing example embeddings. So they are distributed in the same way as real embeddings will be for positions 0, 1, 2, 500, and 10,000, and for different indices like 0, 1, 2, 3, then for index 100, 101, 510, 511, and then we have mean over the entire row, including the hidden numbers, standard deviation, and magnitude of the vector. The same for encodings, and the same for sum. So what will be the result, the resulting sum? And you see that the magnitude of embeddings vector is about 700, and the magnitude of the encodings vector is about 22 or 23, which means that encodings will have some impact on the embeddings vector, but not that high. And the ratio will be about 31, right? So which means that we have 30 pieces of information about semantics and 1 piece of information about encodings. And you may notice that this ratio will be different if we have a different D model. So if the model will be 124 as in big model, then impact of semantics will be even higher compared to encodings. And yeah. And I heard such an opinion that sine and cosine are present in the encoding vector in order to compensate the impact. So if sine will be possible, cosine will be positive, cosine will be negative, and thus there will be no bias. So vector of embeddings won't be changed in mean. But in reality, it is changed just because encodings are not symmetrical. So sine and cosine are not symmetrical. As you have seen, they have this tail over here, at least for first positions, and this tail is mainly positive, and it's positive both for sine and cosine. That's why the mean value of the encoding vector is about 0.5 for early positions. For positions like 500 is already 0.25, and at positions of 10,000, which is quite rare, I believe, it will be about 0. So actually, sine and cosine are needed here not to avoid the bias of shifting the embedding layer vector, but for the reasons I have told you previously. So here is it. And as a result, the magnitude is about the same, though standard deviation, the mean of the embeddings is a bit shifted. So here we had a mean of like 1.12, and here we have mean of 1.61. Which is shifted by this mean of the encodings. And I don't think it's a big problem because they have this layer norm transformation in the architecture. So in any case, this bias will be eliminated if it will be problematic. So not a big deal. Okay, and what more? Yeah, and there is a question of, okay, so they have this, they add they have encodings to embeddings, but why don't they concatenate? And I've heard such an opinion that concatenation is for rich who have access to lots of GPUs, but for poors, a cheaper solution is to add vectors to sum them up so that positional information is added and the size of the model is not increased. But I think it's not correct, because for those who are rich and who can afford these long d-model values like bigger model, it will be still more beneficial to have longer embeddings and add encodings to them, because model quality will be higher in this case, rather than if they will have shorter embeddings and encodings concatenated. So the actual answer is that they are added but not concatenated, because it gives a better balance of resources spent over the resulting quality. I think that's the answer. Okay, so we have covered the block of how encodings are added to the input, and now let's speak about what places inside transformer are impacted by positional encodings, and I will show you exactly the place where encodings are amplifying the nearby positions. So here I have crossed out the layers that are not impacted by encodings, and actually layers that are impacted are attention layers. And in attention layers, main thing that is impacted is this attention, and in attention we have these two multiplications that actually do amplification of attention according to the positional encodings. So as you have already seen, we have matrix multiplication in there, and in the formula it looks like that. And this matrix multiplication will produce higher value in case vectors are more similar. And as you remember, for nearby positions, vectors are more similar and produce higher dot product. And thus, attention will just be higher because we will multiply vector by more similar vector, because positional encodings are similar. And this number will have higher chance to be higher, and thus it will be amplified by softmax. And what is good is that this design of encodings will amplify attention to nearby positions from the beginning of the training. In learned encodings, as in learned positional embeddings, as in BERT or GPT, the model needs to learn some information about position, and only then amplification will happen. But in this case, amplification is done from the beginning. That's the beauty of the mechanism. And yeah, that's how dot product is important. So dot product for positional encodings is higher, which means that dot product of these vectors will be higher. The only thing is that multi-head attention doesn't pass embedding vector exactly to the attention. They have these linear projections before, which means that potentially linear projections may be done in a way that it will harm the positional information, but in some cases it will harm, but in some cases it won't, and still some amplification will happen, which is great. And I find this particular piece pretty beautiful. A small piece of text is dedicated to explanation of positional encodings in the paper, but I believe really huge amount of efforts and attention and energy was put into the design here. And yeah, as you probably understand, that linear projections in these heads may allow for one projection to project embedding indices, like first embedding indices, which have higher frequencies of encodings, of positional encodings, and some other projection for another head may look into like deeper positions which contain to deeper indices of the embedding and encoding, positional encoding, which contain like information about lower frequencies, and thus some heads may amplify closer connections and some heads may amplify like more distant connections. So that's how I understand this intuition. And I also think that probably the first encoder and decoder layers in this stack are more impacted by the encodings, and over time in the next layers when encoding will repeat, probably positional information won't have this high impact, just because it will be already multiplied and converted to some other representations of the information. Yeah, and though still encodings, positional encodings will be propagated through pipeline, because they have these residual connections here, which definitely helps to train to keep gradients stable. But also I believe these residual connections will help to pass positional information over the pipeline, because yeah, they will just keep it if it's important. And this ratio of 30 between embeddings for semantics and positional encodings likely was selected because it is strong enough for the model to notice positional information, but weak enough for the encodings for positional information not to harm too much the information about semantics. Okay, so that's the pre-last block. And now let's summarize what we have, and I will speak about limitations here. But before that, I ask you to press like to this video if you like it, and subscribe to my channel not to miss new similar content. I probably will make more videos about transformer because there are more things to explain, so we'll try to do that. And if you have any questions about encodings or about transformer in general, please write them down in the comment. I will be happy to respond. So let's speak about the limitations and summarize this entire piece of knowledge. So first of all, yeah, there is some limitation is that some semantical information is still lost because embeddings have these positional encodings just added, not concatenated. Though, as shown previously, probably it's the better solution than concatenation. Probably there is an even better solution, I don't know, but this one seems like quite a good compromise. An actual problem, I think, is that this design doesn't benefit from bigger data set. So in deep learning, usually when we add more data, we get better results. But positional information doesn't depend on the input, it's just determined, which means that if we will have better data set, semantical part will benefit, but positional part won't. And I believe that's why BERT and GPT are using learned positional embeddings, because on bigger data set they probably see a bigger improvement. In the paper, authors said that they tried learned, let me see, they said that they tried learned embeddings, though result was almost the same. Actually it was a bit higher. Oh no, actually it was not higher, it was about the same. But it might be higher if the dataset will be bigger. So they trained on some dataset, but if we will have extend more data, then quite likely that learned embeddings will be are outperforming the predetermined ones. And with such a design, distant though strongly related tokens are not amplified. So this heat map clearly shows that diagonal is light, and the more distant the tokens from diagonal, then the smaller will be the amplification of the attention. And probably again that's the reason of why BERT and GPT used learned positional embeddings. And generally we see that positional encodings are needed because the order of tokens is not taken into account, and the way internal representations of the input is changing when we change the order of tokens is not easy for the model to learn. So that's why we need the information to be added, and I have shown you the design of the layers that are in the transformer. So how does it happen that they don't take care of the position? Given positional encodings mechanism, amplify nearby tokens from the beginning without any learning, which is great. And positional encodings magnitude relate to semantic magnitude as 1 to 30. So as I've shown you on an example. So that's it. That was a pretty big piece of information. Hope you will find it helpful, and see you.